Welcome to This Explainer. Today, we're diving into what I like to call a genuine intellectual detective story. We are going to explore the profound motivations and the really incredible journey that led author Francesco Cester to write his fascinating book, Newton and Relativity. Okay, let's just dive right into this. You see, Cester didn't just want to accept the rules of modern physics at face value. He was deeply driven to know exactly why they worked the way they did, and more importantly, he wanted to know if they could be traced back to the classical physics we've all known for centuries. This is a story of intense frustration, sudden epiphanies, and a relentless quest to bridge two seemingly completely different worlds of science.
Now, you might be wondering, if E equals mc squared works perfectly fine in classical physics, why on earth can't we prove it classically? Well, this brilliant question is the exact hook that launched Cester's years-long quest. As a young student, he obviously knew Einstein's famous equation belonged to the theory of relativity, but he also knew that it holds completely unchanged for phenomena within classical physics. So the crucial point for him was this: if it works in the classical world, why does everyone insist it can only be proven using relativistic assumptions? Why couldn't he prove it using the good old classical rules of Newton? That single nagging question became the absolute driving motivation behind his entire life's work.
Section 1. The student's big question.
So, let's talk about Cester's early struggles, because they were incredibly frustrating for him. Since E equals mc squared is, at its core, an equation about energy, his very first instinct was totally logical, right? He relied on the classical law of conservation of energy. But unfortunately, that approach just led to a massive dead end. He failed again and again in his calculations. The math literally just wouldn't work out. It was a really painful wall to hit, but as you'll see, this failure was actually absolutely crucial to push him in a completely new direction.
Section 2. A Wikipedia epiphany.
I absolutely love this part of the story. After basically hitting a brick wall with energy conservation, Cester actually stumbles upon this specific sentence while just casually reading Wikipedia. It read, "An alternative version of Einstein's thought experiment was proposed by Fritz Rohrlich, 1990, who based his reasoning on the Doppler effect. In the moving frame, it has momentum P equals mv." For Cester, seeing those exact words was literally like a lightning bolt. It sparked a massive aha moment.
That little Wikipedia quote? It held the secret key. Cester suddenly realized his massive mistake. In his derivation, he shouldn't have been using energy balance at all. He needed to scrap that completely and instead use an equation based on the conservation of momentum. This was the exact turning point that motivated him to construct a whole new framework from scratch.
And you know, this shift in momentum brilliantly highlights why the optical Doppler effect was so crucial to his thinking. There are three key properties here that already form a bridge straight to relativity. First off, velocity is relative. It really doesn't matter if the light source or the observer is moving. Second, there's no need for a physical carrier medium, which completely does away with the old, outdated idea of absolute space. And third, if velocity were to somehow exceed the speed of light, meaning v is greater than c, the frequency would become a negative value, which is just impossible in physics. So the optical Doppler effect naturally enforces the speed of light limit all on its own.
Section 3. Unlocking Newton's second law.
Okay, so now we're looking at Newton's famous lex secunda, his second law, but in its full absolute form. The mechanical work equals m times v times dv plus v squared times dm. That second term right there, the v squared dm, is incredibly important. In basic high school physics, we usually just assume mass doesn't change, so we completely ignore that second term. But Cester realized that if you keep it, that term mathematically accounts for mass changing with speed. It is literally the missing link that almost everyone completely overlooks.
So Cester is staring at this equation, and he basically can't believe his eyes. By applying his new findings to this classical law, the famous Lorentz factor, which is what dictates how time and space change in relativity, suddenly just appeared in his mass formula. And he did this without ever touching Einstein's relativistic Lorentz transformations. He had to ask himself, is there way more potential in Newton than we ever previously suspected? The answer, he quickly realized, was a resounding yes.
Section 4. The classical relativistic bridge. Once he finally made that Newton connection, this incredible chain reaction of mathematical discoveries just poured out. Let's walk through this logical progression together. Step 1. He proved mass-energy equivalence strictly from a classical perspective. Step 2. He proved that mass depends on speed. Then the real magic happens in Step 3. By taking those first two formulas and substituting them perfectly back into Newton's full lex secunda, it completely unlocked the formula for relativistic kinetic energy. No modern postulates required whatsoever, just pure classical Newtonian mechanics applied correctly.
And his timeline of discoveries just kept on growing. Once he had kinetic energy nailed down, he used a very similar procedure to prove relativistic acceleration for any velocity. Step by methodical step, he was confirming all the core formulas of the theory of relativity, but he was building them entirely from the ground up, using classical physics. He was quite literally proving that the bridge between the two existed.
But to really lock this in, to truly link Newtonian and relativistic mechanics, he needed one more thing. He had to derive the relativistic addition theorem of velocities. Now, at first, this calculation was a total nightmare, just a complicated algebraic mess with tons of terms. Cester actually almost lost hope. But then, as he noted himself, the equations began to cancel out and simplify as if by magic. It beautifully simplified to prove that the constancy of the speed of light isn't just some assumption or postulate we have to accept blindly. It's a principle that is entirely provable by the fundamental laws of physics.
Section 5. Solving the final puzzle. Even with all this amazing success, Cester wasn't fully satisfied yet. To complete his book, he really needed to derive the Lorentz transformations, the rules for how length contracts and time dilates. The traditional methods rely on really complex geometry or, frankly, somewhat arbitrary mathematical assumptions. Cester wanted his method to rely purely on intuitive, physical conservation principles of energy and momentum, staying perfectly consistent with the rest of his work.
But then, he hits this massive paradox. Observers moving at different speeds disagree on time intervals, right? But here is the trap. To classically calculate exactly how much time dilates, you actually already need to know how much length contracts. And to calculate length contraction, you need to know time dilation. It's a completely insoluble loop. So the big question was, how do you break it without using the very relativistic rules you are actively trying to prove?
So, driven by this intense motivation to find a purely logical path, Cester comes up with an incredibly ingenious solution: the orthogonal observer thought experiment. Instead of having his observers move parallel to the action, he imagined them moving orthogonally, meaning at a perfect right angle to the mechanical processes happening. By looking at it from the side instead of head-on, neither observer gets a distorted view of the timeline. It's a really brilliant workaround. So how does this actually break the loop? Well, because the observers are moving at a right angle to the particles, they can define a common time interval. This completely bypasses that messy time dilation problem temporarily. With time standardized, Cester was finally able to derive length contraction directly from his beloved momentum and energy conservation laws. And once he had length contraction, the famous Lorentz transformations just naturally followed. He actually did it. He completed his classical derivation of special relativity. Francesco Cester's entire journey from a frustrated young student to the author of Newton and Relativity really shows us the sheer power of asking why. He was so motivated to not just accept a disconnect in physics, and by refusing to give up, he built a brilliant bridge using Newton's full equations. It leaves us with a truly profound question to ponder. So I'll leave you with this. If Newton's classical laws secretly held the keys to relativity all along, what else is hiding in plain sight in the physics we think we already understand? Thank you so much for joining me on this explainer, and keep questioning the world around you.